Can you see?
Yeah, can you go full screen? Yeah, great.
Yep.
All right.
Can
So,
you hear me? Yeah.
yeah, it's great. Yeah. So our next speaker today is Manuel Artime from Max Planck Institute for Physics, and he will be talking about the emergence of F4-couplings in heterotic type 2A dual string theories. Manuel, please go ahead.
Great. Thank you, first of all, for the invitation. So I can present here this work. And since I'm the last speaker, let me also thank you both for putting this great series of seminars. So I will present in this paper that we put out a couple of months ago, together with my master thesis supervisor, Ralph Hagen, and his PhD student, Adonia Paraskevopoulou. The outline of the talk will be the following. First, I will present you some motivation, some heuristic argument as to why maybe one should expect M theory to be the natural setting in which to obtain full emergence. Then I will quickly give an overview of the main swampland program ingredients that we need in order to analyze our results. And then I will move on into the string theoretic setup that we use and the results of the paper, the emergence of F2 F4 terms. So let me start with this motivation. Consider the following. Consider that we are in small string coupling, and we take a one-loop exchange of open strings, which include the dynamics for the gauge fields and so on. But after applying open-close duality, what we have is just a three-level exchange of closed strings. Of course, what this means is that in string theory, we cannot just have open strings, but we always need to include closed strings as well. In this regime, both open and closed strings are part of our light or perturbative degrees of freedom. So in this case, gravity is not really an emergent phenomena. The leading gravitational order is already present at the three-level exchange of closed strings. Now consider the opposite situation in which we are in a strongly coupled regime. And here now our D-branes are the light or the perturbative degrees of freedom, and the open and closed strings have decoupled. If we consider the same situation, so a one-loop exchange of open strings between two D-branes, and applying the same logic of open-closed duality, what we see is that gravity emerges, or gravity results from a quantum effect, a one-loop exchange. So it is in these strongly coupled regimes, in particular for type 2A, this is the decompactification limit to M theory, where we expect to have gravity as an emergent phenomenon. And this is the M theory limit that we will see later. So with this in mind, let me move on into the swampland program. And although I imagine most of you are familiar with it, let me just quickly overview some key ideas. So first of all, we have the swampland distance conjecture proposed by Uri and Baffa back in 2006. And what it says is that at an infinite distance point in the modular space, an infinite tower of light states arises with masses scaling exponentially in this way with the distance. What this means is that an infinite amount of light degrees of freedom enter our effective description, rendering it invalid. What was later proposed by Lee, Lerche, and Weigand was that there's only two different types of infinite distance limits, either a decompactification limit, in which the lightest tower is that of a Kaluza-Klein tower. So the description that we recover would be a higher dimensional one, or an emergent string limit, in which the lightest tower of states is that of a string tower. Of course, our M theory limit, which is a strongly coupled type 2A, is just M theory in a circle that becomes large. So this is one example of a decompactification limit. Another important concept is that of the species scale. So although one naively expects the effective description to break down at the Planck mass due to strong gravitational effects, what the appearance of these light states from the swampland distance conjecture, what it does is it lowers the UV cutoff of our theory down to what is known as the species scale. This is the original formulation. by now there has been plenty of studies in many different contexts, but for our purposes, this original formulation will suffice. So with these key ingredients, we can already move on into the first formulation of the emergence proposal, which here I'm taking the formulation from Eran Spalti review on the swampland, which is based or motivated on earlier work, two of which I cite here, this Green, Palti, Valenzuela, and Heidenreich, Risudelius. And what it says is that the dynamics, so the kinetic terms for all fields, are emergent in the infrared by integrating out the states down from some UV scale, which must be below the Planck scale. This statement is quite general, and it was first explored in the context of effective field theories. But by now, I would say there are many works that in some way or another have this emergence philosophy in mind. So here I've cited some of them. The first ones are more on this QFT regimes, while there's some other that are related to black hole results or even holography. I try to be somewhat complete here, but sorry if I forgot something. But what we are trying to achieve is something more concrete, and it's a string theory setup in which we can obtain the entire effective action via this emergence procedure. So although this is not possible in any limit, after a series of work between Ralph, Antonia, together with Niccolò Criviori and Alex Gligovic, what they found is that in an isotropic decompactification limit to M theory, and importantly, this is not any decompactification limit, but this particular M theory limit, one expects in this limit that the entire effective action emerges via quantum effects by integrating out the full infinite tower of states with a mass scale that is either at the species scale or below. So this was shown to hold in different setups. First, in the computation of the prepotential in 4 dimensions in n equals 2 supersymmetry, extending the work of Gopakumar-Bafa. First, here it was done in the case of the resolved conifold, so the non-compact case. But let me point out that last week, a paper was put out by Ralph and Alex, where they tackled some of the examples in the case of compact Calabi-Yau's. More similar to this work is the higher curvature coupling R to the 4 in toroidal compactifications of type 2A, so maximal supersymmetry compactifications, extending the work of Greenwood, Perle, Van Hove with this emergence philosophy in mind. So one may ask, what more can we learn by computing a new coupling? And the idea is that in the case of the R to the 4 coupling, there's a nice mathematical property that, in a sense, resonates nicely with emergence. And what was done here was they were able to obtain full results for 7 dimensions or higher, which in a sense give a physical interpretation of this mathematical property, while for 6 dimensions or lower, and through emergence, only partial results were obtained. But one can change the philosophy and argue that the mathematical property, in a sense, motivates emergence. And now what we want to do is the opposite. We want to compute this F4 coupling in 6 dimensions, where such a mathematical property has not been put forward. So in a sense, the emergence proposal serves as motivation to study more in depth these particular string theoretic amplitudes. And in 6 dimensions, a nice case, as we will see later, wrapped D4 branes are heavier than the species scale. So according to the proposal, they should not be integrated out. And this becomes a non-trivial statement in 6 dimensions. So to sum up, our results will be that indeed they are redundant, and this will give a new mathematical property or a known behavior for this particular F to the 4 coupling. So hopefully I've convinced you that it is interesting to look at this term. So let me move on already into the setup. So we consider type 2A on a K3 down to 6 dimensions, 16 supercharges. And we further focus on the orbifold limit T4 over Z2, where a CFT description is completely solvable. We also consider, for simplicity, vanishing B2 flags on the bulk 2 cycles of the orbifold and rectangular tori. This theory is dual to heterotic string theory on a 4 torus, as it was well studied back in the 90s. And one can see this by performing a series of dualities that I'm showing here in this diagram. From the low dimensional point of view, so for the 6-dimensional theory, this is a strong weak duality. And what I want to point out is that in the last step, we have performed a T-duality along a preferred direction. In this case, we have chosen the first direction. And what this does is that it exchanges the radius in heterotic units of the first direction of the 4 torus with the volume modulus on the type 2A. We have further chose a set of Wilson lines that break the original SO32 to U1 to the 16, which on the type 2A side amounts to setting half an integer B2 flags on the vanishing 2 cycles on the singularities of the orbifold. So the CFT is well defined. And it is this U1 to the 16, the gauge symmetry that the gauge fields of our F2 F4 term will be charged under. For our interests, what we care about is the half BPS particle states, which on the heterotic side are the Kaluza-Klein states and the winding modes along the 4 directions of our 4 torus. And after applying this duality chain here, what we see is that these correspond to D0's wrapped D2 branes along the 6 different bulk 2 cycles of the orbifold and the wrapped D4 on the entire orbifold. I've also highlighted here these 2 states. As I was saying before, we need to perform a T-duality along the first direction on our last step. And what this amounts to is to interchange the winding mode along the first direction on the heterotic side to the wrapped D4s on the type 2A side. So with this, we can already move to the particular limit that we consider, this M-theory limit. And what we do, of course, is consider strongly coupled type 2A, which amounts to decompactifying the M-theory circle through this parameter lambda that we send to infinity. The rest of the scalings we have chosen such that the lower dimensional Planck mass, the 6-dimensional Planck mass, stays fixed. So we have a truly gravitational theory, and we have chosen to scale the radii in such a way that the compactification volume this, of the K3 is fixed in M-theory units. With this limit at hand, we can compute the lightest tower of states, which of course will be that of the D0 branes, as they are the Kaluza-Klein modes of this M-theory circle, and the limit that we are considering is just a decompactification limit. They scale in this way here, and now one can compute the species scale for such a KK tower, which is, of course, as one would expect, the higher dimensional Planck mass, the 7-dimensional Planck mass, which in this kind of limit scales the same way as the 11-dimensional Planck mass. Now we can compute also the scalings of the rest of the towers, and what we see is that the wrapped D2 branes along the different bulk cycles of the orbifold scale the same way at the species scale, but the wrapped D4s are parametrically heavier. So what this means, according to the Emergence proposal, the M-theoretic refinement, is that the light states, the states that we need to integrate out, are these D0 towers and wrapped D2 towers, and bound states of them. Or in other words, the contributions from wrapped D4 branes should be redundant for the particular coupling that we are considering. This we can also, of course, translate into the heterotic frame. And what it means is that the light states are made out of all the Kaluza-Klein states and all the winding modes except those along the first direction. Okay, So let's now look at our particular coupling and see if indeed this is the case. So as I was saying, we look at the F2 F4 term of this U1 to the 16 gauge symmetry, which by the way on the type 2A side amounts to or is given in terms of the twisted sector. This F2 F4 term is half BPS protected, so only half BPS configurations contribute to it. That's why I was flashing before these half BPS particle states. And on the heterotic side is a one loop exact, and on the type 2A side it is a three level exact term. This particular higher gauge coupling was already studied in this paper by Kiritsis, Overs, and Pielin back in 2000s, where they develop an expression in terms of Einstein series that we will use. So from now on, I will always be talking about the heterotic frame, and the reason is mostly technical. It's not super important, but to give you an idea, in the heterotic side, we have the distinction between Kaluza-Klein modes and winding modes. So this gives us some bookkeeping power in order to organize the terms that we want to look at. While on the type 2A side, a priori, all the D2 brane wrapping the different directions are on equal footing. So we don't have this distinction. Anyways, this is mainly a technicality, but just keep in mind that from now on, I will be giving everything in terms of the heterotic theory, but one can use the duality map and go to the type 2A side to have the physical interpretation of emergence. And as it was done in this paper, the coupling is fully described by this expression here, where importantly for the duality to hold, this partition function is given as a half BPS partition function in terms of the half BPS Kaluza-Klein unwinding modes only. And this coupling can be expressed in terms of this Einstein series in the vector representation of the T-duality group SO4, which can be expressed as a one-loop integral, a Schwinger integral, in which there are states running in the loop, which are these half BPS states, the winding and the Kaluza-Klein states along the four torus. Of course, because the coupling is half BPS protected, these also need to satisfy this half BPS condition that I've written here. Just as a quick remark, in the same paper, it was also studied the type 2A dual, and what was seen is that the coupling there is given by a similar Einstein series, this time on the cospinor representation of the T-duality group, as it is the representation in which the RAP-D branes transform. So in this sense, also in the type 2A side of things, we still have the Schwinger one-loop integral philosophy, where we have states running in the loop that we are integrating out. Okay, so what we did was to solve this BPS condition here, compute the integral, and what we do is compute every contribution of bound states involving N1 and not involving N1, which is, recall, the heavy states. And after we add up all of the terms, what we see is an explicit cancellation of the terms that involve the N1, the heavy modes. So after applying the duality map to type 2A, what this means is that the D4 brane contributions are redundant, as the emergence proposal predicts. And as I was saying before, this gives us a new property for this Einstein series that was not observed before. Roughly, what it would mean is that the entire Einstein series, our original Einstein series, can be given by a higher dimensional one together with a singlet corresponding to the Kaluza-Klein modes along the first direction. So in this sense, the winding modes along the first direction have decoupled, and we can compute the entire one with this with less amount of states. So just before I conclude, let me show you a bit how the computation that we do goes. So what we have seen is that the coupling can be expressed as a sum of bound states of worldsheet instantons in this way here. where Cij are the wrapping numbers of the worldsheet instantons, wrapping directions ij. And of course, because this is a half BPS protected quantity, also the worldsheet instantons need to satisfy some BPS condition. So as I was saying before, what we do is solve this BPS condition here for different amount of numbers of winding numbers turned on. And we see what these different configurations to what worldsheet bound states of worldsheet instantons they can contribute to. So let me do this with an example that maybe is more clear. Consider the bound state of 3 worldsheet instantons wrapping directions 1, 2, 1, 3, and 2, 3. What we would need is to go back to this expression and solve the BPS condition and the integral for having N1 and N2 turned on, N1 and N3, N2 and 3, and N1, N2, and N3. And what we see after we add up all of these contributions is that exactly those involving N1, which was the heavy state, cancel each other, and the entire term can be obtained by just integrating out the light states. As a quick remark, let me say that the most complicated case of the bound state of 6 worldsheet instantons, we could not compute this exact cancellation, but I have to say that the term that comes from the light states is consistent with the worldsheet, with the expansion that we find for the capping. So in this sense, it seems that everything is working nicely. So let me conclude. Hopefully, I've convinced you that M3 might be the natural limit for an emergent description of quantum gravity, where we can recover the entire effective action. We do this by providing evidence for the M-theoretic emergence proposal, in this case in half maximal supersymmetry in 6 dimensions. We do this by computing the redundancy of D4-brane contributions in this particular F2-F4 coupling. But this also gives us insights into unknown behavior of string amplitudes. And I think this might be something interesting to explore further, to see if there's any other amplitudes that have some behavior that is unknown, and emergence can give us an idea on where to look for these things. And in this sense also, I think the Emergence proposal fits nicely, not only into the Swampland program, but can also be used as a tool to make mathematical predictions, in this case for this Einstein series. And although I haven't shown this here, in the paper we also comment that we have some preliminary results on 5 dimensions. Here, the NS5-branes wrapping the entire geometry are also at the species scale, so they would need to be integrated out. And for simple terms that we consider, we see that indeed the D4-brane contributions drop out and NS5-brane contributions need to be included. Of course, ideally one would want to go into non-BPS protected couplings, but of course this at the moment seems quite difficult, as we are lacking a microscopic description of M theory. Thank you.
All right, thanks, Manuel, for the very nice talk. Are there any questions from the audience? Yeah, please, Ignacio.
Yeah, I have maybe it's like a technicality, but for me it was interesting. You've mentioned that all the time you are working such that you put some Wilson lines that you break the gauge group to U116. Is there like any technical reason why you do it? Why can't you keep the original gauge group?
Well, I think for the CFT, so in order to study, I mean, this was studied in this paper by Kiridis Roberts and Pialin, and I think mainly the reason is to have control in both the heterotic and the type 2A setting. So in order to study this the CFT at the orbifold point in the type 2A side, with the B2 flux on the vanishing 2 cycles on, then you have some U1 symmetry there. And to match this on the heterotic side, you need to break the SO32 to U1 to the 16.
But you
So
could
it's
also have this like if in the type 2A you have like some arrangement of branes such that you don't cancel the tadpole locally, just like by doing like some stacks of the branes, you can also get like a larger engaged group. I guess it's more complicated, but like, is there any reason why it should be maybe more complicated but impossible to do? Or
I'm not entirely sure if then like a geometric description like this in terms of integrating out states comes up as naturally in that case. I'm not entirely sure. I don't know if it has been explored.
okay, thanks.
Yeah, there is another question by Sav.
Hi, Manuel. Thank you for the nice talk. I have a sort of stupid question. I apologize ahead of time. I'm just a little bit confused about can you just say again what the emergence proposal is meant to be? I mean, is
Yeah.
it a statement about supersymmetric
Uh,
couplings, or is it some more general statement about any coupling?
General, I'd say in our case, the entire effective action should emerge by integrating out these light towers of states. Of course, if the particular term that you're looking into is non-BPS protected, more states will enter the integrating out procedure. I don't know if
Okay.
that.
So this is not tied in any sense to weak coupling in some frame.
Well, I mean, this is
I,
an
I think
M-theory limit, so it's strongly coupled.
No, I mean, I think the thing that's bothering me is that normally you would say, I have a quantum description that is good in some regime, weak string coupling, or some dual description that's strong string coupling, but not in between, for example. And you would
Mhm,
use that weak coupling description to compute couplings in spacetime, say, or
mhm,
renormalization. Now, it's true that there are special couplings like these ones, which are basically completely determined by SUSY. This F to the fourth is completely fixed by SUSY. The
yeah.
R to the fourth is completely fixed by SUSY. So they're all completely controlled. And there you can just interpolate back and forth, and there are
Mhm.
different pictures. But I just don't see why that picture should hold if I looked at something that wasn't supersymmetric
I mean, this
or
particular
wasn't controlled that way.
I would say, like, of course, the integrating out procedure, if we are at strong coupling without the microscopic description of M theory, we cannot really do. So, in this sense, of course, we are using this kind of results, but the idea is that this should also hold for the non-BPS protected couplings.
So some kind of determ in the action should also result in the same way from some. I mean, that would be very non-trivial if one could show that.
Yeah.
Because that, there we don't have control in general.
Yeah, of course, but without the description of M theory, I'm not entirely sure how this could be done, I guess.
Okay, good. Thank you.
Thanks.
All right. Let's thank Manuel once again. And